Welcome back to AI Paper Podcasts. We're continuing our deep dive into diffusion models today.
Yes.
And we're going to be tackling a paper that really laid the groundwork for a lot of what we see now.
Definitely a classic.
It's from 2021, called High Resolution Image Synthesis with Latent Diffusion Models.
Yeah, it's a good one.
Now, you might be thinking, 2021, isn't that kind of old news in the AI world?
Cool.
Things move so fast.
Yeah, 3 years ago is ancient history in AI time.
Yeah, exactly. But this paper was really a turning point, and I think it's worth revisiting.
Absolutely. So much of what we're seeing today stems from the ideas in this paper.
Okay, so let's set the scene a little bit. What was the biggest problem researchers were facing back then when it came to diffusion models and image generation?
Well, if you wanted to create high-resolution images with diffusion models, it was a computational nightmare.
Yeah,
Like, you needed a server farm just to get decent results.
I see.
And it was all because traditional diffusion models work directly with pixels. So imagine trying to generate a 1024 by 924 image that's over 1 million pixels.
Whoa, that's a lot.
It is. And every single step in the diffusion process involved crunching numbers for all those pixels, which was incredibly slow and took a ton of processing power.
So training these models was like running a marathon with a refrigerator strapped to your back.
Pretty much. It was a major bottleneck for researchers.
Yeah, I can see that.
But this paper introduced a really game-changing idea, moving the whole diffusion process into a compressed latent space.
Ah, the latent space, one of those terms that gets thrown around a lot in AI.
Right. It's basically a more compact way of representing an image, kind of like a secret code that captures the essence of what's in the picture.
I like that, a secret code.
And this code captures the important stuff without all the pixel-by-pixel details.
Okay, so how did they actually create this compressed space?
They used a special type of neural network called an autoencoder.
Autoencoder.
And it learns to compress the image into a much smaller representation. It's kind of like zipping a file.
Oh, I see. So it finds those redundancies and squeezes them out.
Exactly. But the clever part is that this autoencoder also learns to unpack that compressed representation back into the original image.
So it can go both ways.
Yeah, it's like a two-way street. You can go from the full image to the compressed version and then back again.
Okay, that's pretty cool.
Right. And it does this while preserving the most important visual details along the way.
So it's not just about blindly squeezing the image down as much as possible. It's about finding the most efficient way to represent the image's visual essence.
That's a great way to put it. And, they didn't just settle for one way to shape this latent space.
Oh, yeah.
They actually experimented with different approaches.
Okay, like what?
They tried both continuous methods using something called a KL penalty.
Okay.
And they also tried discrete methods using vector quantization.
I've heard of vector quantization, but I always struggle to picture it.
Well, think of it this way. The KL penalty encourages the latent space to be smooth and continuous, like a landscape with rolling hills. So you can move smoothly from one point to another in this space.
Okay, I can picture that kind of like a gentle slope.
Exactly. But with vector quantization, it's a bit different. It's more like creating a digital paint-by-numbers representation of the image.
Paint by numbers.
Yeah, instead of a smooth landscape, you have a grid of discrete points. And each point represents a specific visual feature or code from a predefined set.
Ah, so it's more structured, almost like building with Lego blocks, where each block has a distinct shape and color.
Precisely. So they essentially gave the diffusion model a choice. Work with the rolling hills or the Lego blocks.
That's a fun way to think about it. So what were the benefits of each approach? Did they find one worked better than the other?
Well, it depended on what they were trying to achieve. They found that both approaches had their own strengths.
Okay.
The continuous approach with the KL penalty, it tended to be more flexible. It allowed for smoother transitions between different parts of the latent space, and that's good for things like generating variations of an image.
So it's like having a brush that can blend colors seamlessly in that rolling hills landscape.
Exactly. You can create subtle shifts and variations.
I see. And what about vector quantization, the Lego approach?
Well, sometimes it led to better image quality, especially for images with sharp edges or distinct textures, because those discrete points could really capture those fine details.
Makes sense, kind of like how Legos can create those really precise structures.
Right. So the choice of which approach to use really depended on the specific task and what you were optimizing for, whether it was speed, quality, or diversity.
So they have this really clever way of compressing images into a more manageable form, but how did the actual diffusion model fit into this?
That's where the magic happens. Instead of training the diffusion model on the original high-resolution images,
Hmm.
they trained it on these compressed representations, these latent codes.
Oh, I see. So it's like the diffusion model is learning to paint a picture, but instead of working with a huge canvas and a full palette of colors, it's using a smaller canvas and a limited set of colors.
That's a fantastic analogy. And what's remarkable is that even though it's working with this simplified representation, it can still generate incredibly realistic high-resolution images when we decode those representations back into pixel space.
So they found a way to make the whole process much more efficient without sacrificing image quality. That's really impressive.
It is, and the speed improvements were really something else. They trained a model with 8x downsampling, which they called LDM8, and it was 38 times faster than a pixel-based model.
38 times. Wow, that's a huge difference.
Right. And that meant researchers could experiment with new ideas and create amazing images without needing access to massive computing resources.
So it really opened up the field to a wider range of people.
Exactly. And it wasn't just about training. Generating new images was also much faster.
So this latent space approach was like hitting the fast forward button on the whole process.
Precisely. And here's the thing. Despite working in this compressed space, LDMs often produced higher quality images than pixel-based diffusion models.
Wait, higher quality? I would have thought compressing the images would lead to a loss of detail. How did they manage that?
It's all about this idea of perceptual compression.
Okay, tell me more.
Traditional compression methods often try to preserve every single pixel,
Yeah.
even if those pixels contain information that we humans can't even perceive.
So it's like those high-frequency details that you might not even notice unless you zoomed in really close.
Exactly. It's like trying to compress a song by preserving every tiny fluctuation in the sound wave, even the ones beyond our hearing range.
Which would make the file huge.
Exactly. But LDMs, they focused on preserving the features that humans find visually important. Things like edges, textures, overall composition.
The stuff that really makes an image pop.
Exactly. It's like they learned to see the image the way we do, filtering out the unnecessary noise and focusing on the essence of the visual experience.
That's brilliant. They taught the model to work smarter, not harder.
Exactly. And they even took this a step further with what they call two-stage compression.
Okay, two-stage compression. Now I'm intrigued. What's that about?
They broke down image learning into two distinct stages.
Okay.
The first stage involves removing those imperceptible details, kind of like zipping a file to remove redundancy.
Got it. So that's the initial compression step.
Right. And then the second stage, that's where the real magic happens.
What happens in the second stage?
This is where the model learns the semantic composition of the image, the relationships between objects and concepts.
So it's going beyond just pixels and colors and starting to understand what the image is actually about.
Exactly. It's like applying a more intelligent compression algorithm that understands the content of the file.
So it's not just about blindly squeezing the information down. It's about understanding the underlying structure and meaning.
Precisely. And this two-stage compression idea was a key insight that allowed LDMs to be both efficient and high fidelity.
This is fascinating stuff. But I'm curious, they talked about training models with different downsampling factors. Wasn't there a sweet spot? Too much compression and you lose too much detail.
You're absolutely right.
Too little and the model becomes slow to train.
Exactly. Finding that balance was crucial.
So what did they find?
They experimented with different downsampling factors and found that, generally speaking, 4x and 8x downsampling struck the best balance between quality and efficiency.
Ah, so it's like Goldilocks in the porridge. Not too hot, not too cold, just right.
Exactly. You don't want to compress too much or too little. You want to find that sweet spot.
Okay, so this all sounds pretty amazing from a research perspective, but did this have any impact on the real world? Could people with regular computers actually use these LDMs?
That was one of the most exciting things about this paper. By making high-resolution image generation more accessible, it opened the door for artists, designers, anyone with a creative spark to actually use these tools.
It's like they democratized access to cutting-edge AI.
That's a great way to put it. And there's another cool thing.
What's that?
The latent space itself, the one created by the autoencoder, it's reusable. You can train one autoencoder and then use its latent space for multiple tasks, not just image generation.
So it's like a master key that unlocks a whole suite of AI tools.
Exactly. You could use it for image generation, super resolution, inpainting, all sorts of things.
A Swiss Army knife of AI possibilities. Okay, so they've got this amazing framework for making diffusion models faster, more efficient, even higher quality.
Right.
But let's talk about the really fun part. The
I
applications.
know, let's get to the cool stuff.
They didn't just stop at the theory, did they?
Absolutely not. They pushed the boundaries and explored a whole range of tasks.
Like what?
One of the most exciting ones was text-to-image synthesis.
Ah, yes. Being able to type in a description and have the AI conjure up an image based on your words. It sounds like something out of a sci-fi novel.
I know, right? And back then, this was still pretty early days for this kind of technology.
So you couldn't just type in something crazy like a cat wearing a top hat riding a unicycle on the moon and expect it to work perfectly.
Well, maybe not that specific,
Okay.
but they showed that LDMs could capture the essence of a text description
Hmm.
and translate that into a pretty compelling image.
Still pretty impressive for the time.
Oh yeah, definitely groundbreaking.
What other applications did they explore?
Well, they also looked at something called layout-to-image synthesis, where you give the model a basic layout with bounding boxes and class labels like car, person, building, and it fills in the details to create a realistic image.
So it's like giving the model a rough sketch and letting it bring it to life.
Exactly. And they actually achieved state-of-the-art results for this at the time.
Wow. What
They also tackled super resolution, upscaling low resolution images to high resolution with remarkable clarity.
Hold on, state of the art. They managed to beat specialized super resolution models using a more general LDM.
They did. It was pretty surprising at the time, really showed the power of this approach.
That's amazing.
And they didn't stop there. They also looked into inpainting.
Inpainting.
Yeah, filling in missing parts of an image. Think about restoring old photos with damage or removing unwanted objects.
Oh, I see, like those old family photos with rips and tears.
Exactly.
So did they achieve state-of-the-art results there too?
They did. LDMs just seem to excel at all these different tasks.
It's really impressive how versatile they are.
And one more thing I want to mention, they explored something called convolutional sampling.
Okay, convolutional sampling.
Yeah, it's a technique that allowed them to generate images larger than the resolution they were trained on.
Wait, so they could create these giant high-res images even if the model had only seen smaller images during training?
Yep. It's a bit technical, but basically they conditioned the model with spatially aligned information, like a semantic map or a low-res image, and then used convolutional operations to stitch together different parts of the image.
So it's like creating a giant puzzle and figuring out how to assemble the pieces using AI.
A great analogy. And this opened up some really exciting possibilities for creating large, detailed images with LDMs.
This is incredible stuff. It's no wonder this paper is considered a classic.
Definitely a landmark paper. And to get a better sense of the visual magic they achieved, be sure to check out the show notes for some examples of their results.
Oh, I think our listeners are definitely going to want to see that. Okay, so we've covered the high-level concepts and the impact, but I have a question. This paper was published in 2021, which, as we said earlier, is practically ancient history in the world of AI. How has it held up?
It's aged remarkably well.
Right.
Yeah, this paper was incredibly influential. It didn't just introduce a clever trick, it introduced a whole new way of thinking about diffusion models.
Okay.
And the idea of learning in a compressed latent space, that's become a standard technique, not just for image generation, but for other areas of AI as well.
So its impact is really extended beyond just pretty pictures.
Absolutely. This paper was a pivotal moment that shifted the landscape of what's possible with AI.
It's like this paper was the zip file that compressed years of research into a format that the AI community could easily access and build upon.
I love that analogy. That's a great way to put it.
Okay, we talked about the high-level concepts and the impact, but when I was reading the paper, there were a few intriguing details that caught my eye.
Oh, I'm curious, what piqued your interest?
Well, you mentioned they achieved some impressive results on ImageNet,
Yeah, ImageNet.
which is a massive data set that's often used as a benchmark for image recognition and generation models. What was so special about their results?
ImageNet is notoriously challenging. It contains tons of images, a huge variety of objects and scenes, and for LDMs to achieve state-of-the-art results on ImageNet, even with this compressed latent space, that was a big deal.
So they were going head-to-head with the best models out there and still coming out on top.
Exactly. It really showed the power of this approach, even back then.
That's amazing. They were essentially working with a smaller canvas and still managed to outperform models using the full palette of pixels.
It's a testament to the efficiency and effectiveness of learning in that compressed latent space.
Also curious about the trade-off of compression. You mentioned they experimented with different downsampling factors.
Yeah.
What did they find? What was the sweet spot?
Finding that balance was key. And what they discovered was that for image generation, compressing too much, like with a downsampling factor of 32, it actually hurt the final image quality.
How interesting.
It's like trying to cram too much information into a tiny zip file. You're going to lose something in the process.
So there's a limit to how much you can squeeze the information down without sacrificing quality.
Exactly. On the other hand, using a very small downsampling factor, like of 2 or even no downsampling at all, made the training process super slow.
Even if the final image quality was a bit better.
Yeah, it seems like that sweet spot for high-quality results and reasonable training time, it was somewhere between 4x and 8x downsampling.
So finding the Goldilocks zone was important. Not too much compression, not too little.
Exactly. And they also talked about incorporating conditioning into the LDM framework.
Conditioning?
Yeah, they weren't just generating random images. They wanted to control the generation process.
Right, to create images based on text prompts, layouts, even low-res images for super resolution.
Exactly. It's like giving the model a set of instructions or a blueprint to follow.
Okay, but how did they do that without making things overly complicated?
They use this clever mechanism called cross-attention to inject that conditioning information into the diffusion model.
Cross-attention, okay. Explain it to me like a 5.
Okay, so imagine the diffusion model is like a composer writing a symphony.
Okay, I like this analogy.
The denoising process is like adding notes to the score, gradually building up the musical piece. Now, cross-attention is like giving the composer some sheet music from another piece, a melody or a chord progression to use as inspiration.
So the composer is still in control, but they're using this external sheet music as guidance.
Exactly. And in the case of LDMs, that external information also comes in the form of those compressed representations, just like the images themselves.
Okay, so if you're doing text-to-image generation, you have the latent representation of the image and the latent representation of the text prompt, and they're both sort of feeding into the model.
That's exactly right. And that cross-attention mechanism, it allows the model to selectively pay attention to different parts of the text prompt at different stages of the denoising process.
Because it's not just blindly copying the text prompt, it's thoughtfully weaving it into the generation process.
Precisely. And that's how they got those impressive results, where the generated images not only looked realistic, but they also made sense in the context of the text prompt or the layout or whatever conditioning information they were given.
It's like they create a whole new language for AI to understand and respond to different forms of information.
It really is a groundbreaking development, and it's been so cool to see how researchers have built on these ideas to create even more powerful and versatile AI models.
Okay, so we've covered the autoencoder, the diffusion model, and this amazing cross-attention mechanism.
Right.
But I remember you mentioning different ways to shape the latent space itself. Those were called KL regularization and VQ regularization.
Ah, yes, good catch.
Could you explain those a bit more?
Absolutely. Remember how we talked about the latent space being like a landscape?
The rolling hills and the Lego block?
Exactly. Well, KL regularization, it encourages that landscape to be smooth and continuous, like rolling hills.
Okay.
It prevents the latent space from becoming too jagged or discontinuous, which can cause problems during generation.
So it's all about making sure the diffusion model can move smoothly through that latent space.
Precisely. And the smoothness helps to ensure that the model can generate diverse and realistic images.
Makes sense. And what about VQ regularization? You mentioned it uses vector quantization.
Right, vector quantization. Think back to that analogy of the box of crayons.
Each crayon representing a distinct point in the latent space.
Exactly. Instead of crayon colors, we have these codebook vectors, which are like specific points in that latent space.
Okay.
The encoder maps each part of the image to the closest codebook vector, creating that digital paint-by-numbers representation we talked about.
So it's like converting a smooth landscape into a grid of discrete points.
Exactly. And this approach, believe it or not, sometimes led to even better image quality.
Really?
Yeah, especially for images with sharp edges or distinct textures. Those discrete points could really capture those fine details.
It's like giving the model a set of Lego blocks to play with.
Precisely. And it can combine and arrange those blocks in the latent space to create all sorts of different images.
That's fascinating. So the choice of which regularization method to use really depended on the specific task and the desired balance between quality, diversity, and computational cost.
You got it. They were always looking for the best tool for the job.
This is all so fascinating. It's amazing to see how all these pieces come together to create such a powerful framework for image generation.
It really is. And while this paper focused primarily on image generation, the contributions went way beyond that.
In what way?
Well, their insights into latent spaces, compression, and denoising, they've had a huge impact on other areas of AI as well.
So it wasn't just about pretty pictures. It was about changing the way we think about AI.
Exactly. And, in the next part of our deep dive, we're going to explore how LDMs revolutionize things like inpainting and super resolution.
Oh, I can't wait to hear more about that.
Get ready for some serious AI magic.
I'm excited.
Welcome back to AI Paper Podcasts. Are you ready to get under the hood and see how these LDMs really work?
Absolutely. Part one got me hooked. Let's start with that autoencoder, the neural network that compresses those images into that efficient latent space. What made their architecture so special?
Well, the architecture itself is actually pretty straightforward. Both the encoder, the part that compresses the image, and the decoder, the part that reconstructs it, they were both built using convolutional neural networks.
Convolutional neural networks, those are like the workhorses of computer vision, right? They're great at finding patterns in images.
Exactly. They're designed to capture those spatial relationships and hierarchical features in images,
Right.
which makes them a perfect fit for this task.
That makes sense. But training an autoencoder to find that perfect balance between compression and fidelity, that must have been tricky. How did they do it?
They used a clever combination of loss functions to guide the training process.
Okay.
One really crucial element was the perceptual loss.
Perceptual loss.
Yeah, it's not just about matching the pixels exactly. It's more about making sure that compressed representation captures those high-level features that matter to us humans when we look at an image.
So it's not just about recreating a pixel-perfect copy. It's about preserving the things that make an image look visually appealing and realistic to us humans, right?
Exactly. Think about edges, textures, overall composition, the things that our brains naturally pick up on when we look at an image.
Okay, so how do you teach a neural network to see the way humans do?
Yeah. They actually used a pre-trained image classification network like VGG to calculate this perceptual loss.
At EGG.
And these networks are already trained to recognize a huge variety of objects and scenes, so they have a pretty good understanding of what visual features are important for us.
So it's like having an expert art critic judge the quality of the compressed representation.
I like that analogy. Yeah, they're leveraging that knowledge that's already baked into these powerful image classification networks to guide the autoencoder's training.
That's clever, but it sounds like perceptual loss alone wouldn't be enough. You'd also need to make sure that the reconstructed images actually look realistic at a more detailed level.
You're absolutely right. That's why they also incorporated an adversarial loss, which is a technique that they borrowed from generative adversarial networks, or GANs.
Jansons. Those are the rock stars of the AI art world, aren't they? They're known for creating those hyper-realistic fake images.
Exactly. And in this case, the adversarial loss, it helps ensure that those reconstructed images actually look convincing even when you zoom in and look at the fine details.
So it's like having a second art critic. But this one is really good at spotting tiny flaws and inconsistencies.
You got it. It's a dynamic duo of art critics working together.
So one loss function that focuses on the overall perceptual quality, the big picture, and another one that makes sure all the little details are right. It's like a powerful combination.
It is. And by combining these losses, they were able to train autoencoders that could significantly compress images while preserving enough visual information for, high quality image generation.
Okay, so the autoencoder, it sets the stage, creating this efficient latent space.
Yeah.
But now let's talk about the star of the show, the diffusion model itself. You mentioned that it's trained on these compressed representations. But what exactly is a diffusion model and how does it work?
Imagine you have a pristine image, right? A diffusion model starts by gradually adding noise to it step by step until it becomes just pure random noise, like static on a TV screen.
So it's like watching a beautiful painting slowly fade away.
Precisely. But here's the cool part. The diffusion model learns to reverse this process.
Oh, really?
Yeah, it starts with that pure noise, and then it learns to gradually remove that noise step by step until it reveals a realistic image. It's like taking that statusy TV screen and slowly bringing a picture back into focus.
Okay, so it's learning to unnoise an image. But how does it know what the original image should look like? It's starting with random noise after all.
That's the key insight. During training the diffusion model, it's shown pairs of noisy images and their slightly less noisy counterparts,
Okay.
And it learns to predict the direction and magnitude of the noise that needs to be removed at each step.
So it's like playing a game of hot and cold, where the model keeps refining its strategy until it gets closer and closer to that target image.
I like that. That's a great way to think about it. And, the brilliance of LDMs, it really lies in applying this denoising process to those latent representations that are produced by the autoencoder.
So instead of trying to denoise millions of pixels. It's working with a much smaller set of values that capture the essence of the image.
Exactly, and that's where the efficiency comes in by working in this compressed space. The diffusion model can learn and generate images much faster, even with limited computing power.
So the autoencoder and the diffusion model, they work in perfect harmony. The autoencoder finds that efficient latent space, and the diffusion model learns to create magic within that space.
It really is a beautiful partnership, and to make things even more interesting, they introduced that cross-attention mechanism that we discussed in part one.
Right. Cross-attention, it allows us to guide the generation process by giving the model, additional information like text prompts or image layouts.
Yeah.
But I'm still a little fuzzy on how that actually works. How did the diffusion model integrate this external information while it's busy denoising?
Okay, imagine the diffusion model is like a composer writing a symphony. Okay, the denoising process is like adding notes to the score, gradually building up the musical piece.
Okay, I'm with you.
Now, the cross-attention mechanism is like giving the composer some sheet music from another piece, maybe a specific melody or chord progression.
So the composer's still in control, but they're using this external sheet music as inspiration or guidance.
Exactly. In the case of LDMs, the external information, it comes in the form of those compressed representations, just like the latent representations of the images. So if you're doing text-to-image generation, you have the latent representation of the image and the latent representation of the text prompt.
So during the denoising process, the diffusion model is looking at both the noisy latent representation of the image and the latent representation of the text prompt.
That's right. And the cross-attention mechanism, it allows the model to selectively pay attention to different parts of the text prompt at different stages of that denoising process. It's like the composer deciding which parts of the external sheet music to incorporate into their own symphony at different points in the piece.
So it's not just blindly copying the text prompt, it's intelligently weaving it into the generation process, guided by that denoising objective.
Precisely. And that's how they achieve those really remarkable results, where the generated images are not only realistic, but they're also semantically aligned with the conditioning information, whether it's text or layout or something else.
It's incredible. It's like they've created this whole new language for AI to understand and respond to different forms of information.
It is a groundbreaking development, and it's been really exciting to see how researchers have built on these ideas to create even more powerful and versatile AI models.
Okay, so we've covered the autoencoder, the diffusion model, and this amazing cross-attention mechanism. But I remember you mentioning different ways to shape the latent space itself.
Yes.
You called them KL regularization and VQ regularization. Could you explain those a bit more?
Absolutely. Remember how we talked about the latent space being like a landscape?
Yeah, the rolling hills and the Lego block.
Exactly. Well, KL regularization, it encourages that landscape to be smooth and continuous, like rolling hills.
Okay.
It prevents the latent space from becoming too jagged or discontinuous, which can cause problems.
Gotcha. So you're basically smoothing out the terrain so the diffusion model can easily navigate it.
That's a great way to think about it. Yeah, this smoothness helps ensure that the diffusion model can generate those diverse and realistic images.
Makes sense. And what about VQ regularization you mentioned? It uses vector quantization.
Right, vector quantization, think back to that box of crayons analogy.
Each crayon representing a specific point in the latent space, right?
Exactly. Instead of crayon colors, we have these codebook vectors, which are like specific points in that latent space.
Okay.
The encoder maps each part of the images to the closest codebook vector, creating that digital paint-by-numbers representation we talked about.
So it's like converting a smooth, continuous landscape into a grid of discrete points, each point representing a specific visual feature.
Exactly. And surprisingly, they found that this approach sometimes led to even better image quality, especially for images with sharp edges or distinct textures. It seems like the diffusion model sometimes benefited from having this more structured, discrete representation to work with.
So it's like giving the model a set of building blocks to play with. It can combine and arrange these discrete elements in the latent space to create a wider range of images.
That's a perfect analogy. And the choice of which regularization method to use, it really depended on the specific application and the desired trade-offs between quality diversity and computational cost.
This is also fascinating. It's amazing to see how all these different pieces come together to create such a powerful framework for image generation.
It really is remarkable what they achieved. And, while this paper focused primarily on image generation, their contributions extended far beyond that.
Oh, in what way?
Well, their insights into latent spaces, compression, denoising, they've had a profound impact on other areas of AI as well.
So this wasn't just about pretty pictures. It was about fundamentally changing the way we think about AI and its capabilities.
Exactly. And in the next part of our deep dive, we're going to explore how LDMs revolutionized image manipulation tasks like inpainting and super
Oh,
resolution.
I can't wait.
Get ready for even more AI magic.
Welcome back to AI Paper Podcasts. We've been on quite a journey with these latent diffusion models, exploring their efficiency, their elegance, and even their ability to, understand text prompts and things like that.
Yeah, it's been fun.
But I'm really excited to see how this all translates into practical applications.
Me too. LDMs weren't just about generating pretty pictures.
Right.
They were actually surprisingly good at all sorts of image manipulation tasks. Things that you might not expect a generative model to be able to handle well.
Like what? Give me some examples.
Well, one area where they really excelled was in painting.
In painting.
Yeah, which is basically, filling in missing parts of an image.
Okay.
Think of those old photos with tears or scratches. LDMs could actually reconstruct those missing areas seamlessly.
That's pretty amazing. So instead of painstakingly retouching those damaged areas by hand, you could just let an LDM do the work.
Exactly. Remember how we talked about the diffusion model gradually removing noise to reveal an image? Well, for inpainting, you essentially apply that same denoising process. But instead of starting with pure noise, you start with an image that has holes or missing regions.
So the LDM treats those missing parts as noise and tries to fill them in based on the surrounding context. It's like the model is an art restorer, carefully reconstructing those missing pieces of a masterpiece.
I like that analogy. That's a perfect way to put it. And the results were really remarkable. They showed that LDMs could achieve state-of-the-art performance on these inpainting tasks, producing really realistic and seamless results, even when large chunks of the image were missing.
That's incredible. So you could use this to, restore old family photos, remove unwanted objects from pictures, or even create entirely new images by starting with a rough sketch and letting the LDM fill in the blanks.
Exactly. And remember that convolutional sampling technique we talked about?
Yeah, the one that let them generate images larger than the training resolution.
That's the one. Well, they applied that to inpainting as well.
Really? So they could take a high-resolution image with a large missing area and use an LDM to fill it in, even if the model had only seen smaller images during training. That's pretty mind-blowing.
It is. It's like having an AI that can extrapolate beyond its training data and kind of imagine what those missing details should look like.
That's incredible. It's like they gave image editors superpowers.
Yeah.
What other image manipulation tricks did they have up their sleeve?
Well, another area where LDMs really shined was super resolution. Taking those blurry, low-resolution images and upscaling them to crisp, high-resolution versions.
Ah, yes. The classic enhance button from all those crime dramas finally brought to life.
Yeah.
But seriously, how did they manage to pull that off?
It goes back to that cross-attention mechanism, the one that let them guide the generation process with additional information.
Right.
Well, they use that to condition the LDM on the low-resolution image itself, effectively giving the model a blueprint to follow as it generated that high-resolution version.
So it's kind of like giving the model a blurry sketch and asking it to fill in all those missing details, but instead of a sketch, it's an actual low-res image.
Exactly. And the results were honestly astonishing. They found that LDMs could actually outperform those specialized super resolution models in some cases,
Really?
even though they weren't specifically designed for that task.
That's really impressive. It seems like instead of having a separate AI model for each image manipulation task, you could potentially use a single LDM to handle a whole range of jobs. It's like the Swiss Army knife of image editing tools.
I love that analogy. And they even explored different ways to guide that super resolution process. They could use like a simple pixel-wise loss function to encourage the model to match that high-resolution target image as closely as possible.
Okay.
But they also experimented with those, more sophisticated perceptual loss functions we talked about earlier.
Right, the ones that focused on preserving those high-level visual features that are important to human perception. So it's not just about adding more pixels, it's about adding the right pixels,
Yeah.
the ones that make the image look more realistic and appealing.
Exactly. And they found that using those perceptual loss functions could actually lead to even better results, producing super resolved images that were not only sharper but also more pleasing to the eye.
It's kind of incredible to think that a model designed for image generation could be so good at image manipulation. It's like they discovered this hidden talent that no one knew LDMs possessed.
It really is a testament to the power and flexibility of this whole framework that they developed. And, it really speaks to the importance of thinking outside the box when it comes to AI and exploring the full potential of these models.
So it seems like LDMs can handle inpainting, super resolution, all sorts of image manipulation tasks, all while maintaining that high quality and efficiency. Is there anything these models can't do?
Well, they're not perfect, of course. Like any AI model, they have their limitations. They can sometimes struggle with, really fine-grained details, or they might produce some artifacts, especially in challenging situations.
Right.
And the sequential nature of that diffusion process means they can still be a bit slower than some other image generation methods, like those speedy GANs we talked about.
Right. Jans are known for their speed and realism, but they can be a bit uh, temperamental to train sometimes.
That's very true. There's always a trade-off, right?
Yeah.
But despite those limitations, I think it's safe to say that LDMs really represent a huge leap forward in the world of image generation and manipulation. They opened up all sorts of new possibilities for researchers, for artists, and really anyone with a passion for visual creativity.
It's amazing to see how this seemingly simple idea of denoising led to such a powerful and versatile framework. It really highlights the ingenuity of those researchers who developed these models.
It really does. This paper was truly groundbreaking, and, it's inspiring to see how the field continues to build upon those ideas even today.
Yeah, I can't wait to see what the future holds for diffusion models. And for our listeners who are feeling inspired to, explore these models themselves, we've included some resources in the show notes to get you started.
Yeah, there are tons of great tutorials, code implementations, and even pre-trained models available online. So, go forth and create.
And that's a wrap on our deep dive into latent diffusion models. Thanks for joining us on AI Paper Podcasts. We'll be back soon with another exciting exploration of cutting-edge AI research. Until then, keep learning, keep exploring, and keep creating.